Hi and welcome back to this latest video that we're doing here. So this is part 2. If you want to know what this video is really about, I'd encourage you to go and watch part 1. We managed to get this far, going Arduino development board with an Atmel 328P MCU in there, little speaker, LCD display, and we've got this breadboard situation at the back here, which is total mess of wires. And let's get this entered into KiCad as a schematic diagram for starters, and then once we've done the schematic diagram we can then have a look at designing a PCB, because we want to put this in a box. Okay, here we are in KiCad, and I've just created a brand new project, and we've called it let's have a look here, called it PCB tester version 1. The LCD display that we want to use, LCD 20 by 4, 20 characters by 4 lines, it doesn't seem to be included in the default library within KiCad. What we're trying to do is download the for this display here, which looks exactly like the display that we're using, and I've got 2 or 3 of these that I bought. Okay, now I have to log in, so stand by. Yeah, so I'm now logged in, and let's go and download the symbol and footprint. So if we do that, KiCad. Now, well, we're using version 8, so let's select 6 or later, and let's have a look, and there's our output files up here. So let's close all this down and go and have a look at this zip file that we've just downloaded. Okay, so once you've downloaded the zip file, you'll notice the contents of the zip file is you've got a KiCad mod there. I think I'll try and zoom in a bit, hang on, and open it up, have a look into the contents of the zip file. You'll notice you get some files, and here's one which is a KiCad underscore mod file. You've also got a KiCad symbol file, that's for schematic. There's also a handy little how to import .htm file here. You can click that and it will explain how to do it. Okay, so I'm going to skip that. I'm just going to go ahead and do this and import it into the project. We'll be right back. Here we are back in KiCad, of course, schematic editor. So let's place our new symbol. Okay, add a symbol. Now you'll notice these are the ones, if you type in character display, these are the ones that KiCad has already loaded. You will notice here we've got a new one, that's LCD 20 by 4B, B for blue. Let's click that one. We've now got a brand new schematic symbol, and it's got all of our data pins on the display, got VDD, VSS. So there's our new symbol, which you can pull into KiCad, and there it is. So now we can place this on the diagram, and there's our brand new symbol for the 20 by 4 display with all the pins that we want. If we open up the PCB editor and just pull everything in and say, got to annotate it first and say update PCB, and then close, and there is our display as a footprint. Okay, so we've got the 4 mounting holes for the to basically bolt the thing down, and we've got the 16 pins at the top there. We've got the layout of the actual display. Let's continue putting some parts. So I'll just save this. There you go. Let's place another part, and we're going to need an LM317. This is going to be our there it is. Place that on the diagram. So we've got our display. We've got the TO220 version of an LM317 current limiter, which of course is actually a variable voltage regulator, but as you know from the earlier video on part 1, we're going to configure this as a current source, as a current limiter. Let's get the MCU sorted out. So we'll want a 328P, which is an Atmel. So let's have our processor here. Okay, and let's stick the display up here. Now you know that 4 of the lines of the LCD display are going to connect to 4 of the lines of the MCU. We could potentially flip this the other way like that by using the flip buttons up here, okay, and then it means we're going to get a neater diagram. Crystal, 2-pin crystal, yeah, okay. Different symbols for crystals here, and crystal small, probably just one of those, I would imagine. None of these have got footprints, interestingly, so we're going to have to assign a footprint by the looks of it anyway. So let's have that. Okay, that's going to go to the crystal pins of the MCU. You see you've got the standard C, which is unpolarized capacitor there. This one's also unpolarized, which is what we want, and it's just going to be a ceramic, you know, surface mount, but it's a smaller symbol, so it's just a smaller symbol on the diagram. So let's zoom out again. So we want 2 of these going to ground, and you can drag individual, you know, labels around for various for various parts. 22P, 22PF in other words, and we can move these around, these labels. Power label, where are we? Add power. Ground is classed as power, and that's going to be a ground connection. Okay, and we can just pull that in a bit there. Yeah. So what I'm going to do now is keep going. We'll do a cut, and I'll add more components, and we'll come back with a bit more circuit diagram. So as you can see, we've added some extra components. So we've got a little preset resistor here for the contrast. This basically is just an adjustment between ground, or 0 if you like, and plus 5 volts. You'll notice we've got these lines here, DB4 to DB7, and we're not using DB0 to DB3. We're only using 4 data lines. There are 2 ways to operate this display. You can have an 8-line display, which gives you faster updates. You can get, you know, more data to it in one chunk. But the standard way of doing it, and it's less connections basically, is just to use the 4-wire system, which only uses DB4 to DB7. We'll have a crystal, which is a 16 megahertz crystal, and this is got a couple of capacitors which goes to ground. So we've got this 6-pin ISP header, and this is, we've shown this before in other projects, it's pretty standard, and I'll not go through it all again, but this allows us to program the MCU externally using an external ISP programmer device, which plugs into here, and then you use these lines here, and then you can upload your firmware into the chip. Now the other thing, of course, moving along a bit, we've got some connectors here. You'll notice we've got an RX-TX connection here, and I did this exactly the same from one of our previous projects for the CTCSS repeater, and it's something I just tend to do automatically without thinking too hard about it. Just basically make sure we've got the comms TX-RX connected, and that goes to PD0, PD1 of the chip. This allows us to get some serial data in and out of the chip. It's handy if you want to maybe do some remote logging, if you want to do some diagnostics, anything we can think of might come in handy. We can convert this to RS-232 if we wish, and send it through a serial cable to a PC or to a terminal. Right, moving along, we have the all-important constant current source and ADC voltmeter, if you like, reading the voltage across the probes. That then supplies power to the probes. This will be a little connector which then goes to 2 probes on the box case. Measuring across the probes, of course, we've got the ADC, which is the Adafruit ADS1115 module, and this is the way we've got it. You'll notice we've got A0 and we've got A1. These are our differential inputs. SCL SDA is our I2C bus, and these 2 wires here go directly to here, which is PC4 and PC5 of the MCU, and this is the SCL SDA lines of the chip. Let's just have a quick look at this. Now, I haven't done anything PCB wise at all. Here we are in the PCB designer, and the first thing we want to do is pull everything in. So this icon here allows us to import in the schematic. Now, we've seen this before in previous videos. All these blue lines are what's called rat lines, and this is electrical connections that it knows that it has to make, but these are not PCB tracks. That's why they're extremely thin. Then they are not copper tracks in any way. These are just rat lines, and eventually when we come to auto route the board, these will be turned into copper tracks. That's where we are now. What I was thinking was, because the display has its own PCB, this is the outline of it just there. Okay, I'm sort of going around it there with the cursor key, and I'm thinking, why don't we make a board which exactly matches the size of the display, okay, with the same mounting holes. In fact, we can copy this and use it as a template. The intent is to build a board, a daughter board if you like, to go on the back of this, and it will match up the dimensions of the board. Maybe makes one side a bit longer so we can put some controls on it perhaps, and we need a matching socket, header socket, on the PCB that goes on the back of this. Okay, so we're going to end up with two boards, one there and one there. Hope that's clear. So one thing we need to do in KiCad is to recreate the footprint the same as the LCD display module, and then we can get the mounting holes exactly correct, and also the position of the header there of the connector. So that will then plug into the back of the LCD unit, and we'll end up with a sort of like a module with two boards. So the whole thing will just go clunk, and then we can use some nuts and bolts or some standoffs perhaps to get the distance right, and yeah, should be neat. Okay, so we've made some nice progress here. We have added this, which is an encoder wheel, and we can use this to set the resistance set point for the lower limit, and you can turn it clockwise or anti-clockwise, and it gives various pulses to the out of phased pulses to the MCU, which then can determine which way you've turned the wheel. If you remember, there was a big display module here for the 20x4 LCD display. Now, because we don't really want the display as part of our PCB design, this is a separate board which goes on the back of the display. We really just want a connector to the display, and that's exactly what this DispCon 16-pin connector is going to do. This is going to be a socket. This will be soldered to the PCB, and this will accept the pin side of it, the male side of the LCD, plugging into this. So let's go and have a look at what we've got with the PCB. Let's take a look at that. And as you can see, I've been doing some work already. This is our PCB now. These are the components roughly where we want them. This may change, and we haven't got any copper tracks yet. So we're just, you know, moving components around, selecting a component, sort of going, yeah, maybe put it in there. We could also put it down here, or we could put it up there even. It may even be better up there. I was just trying to keep the try and keep the ADC pins close to the inputs here. That'll be the probes coming in here, so it gets its constant current source, and it's also reading the voltage from that and going to the one of the inputs onto the ADC there. And to be honest, I think we're pretty much we're in a good position now to start doing tracks. We've got the connector on the correct side. We've got the what would be the rotary switch in there, the rotary encoder in there. So that all looks good. Right, so let's start by doing a quick pass with the auto router, and I haven't defined any class information yet for the track widths, so we're just going to be getting a default track width, which is probably too thin for the power supply. We haven't set up any ground planes or anything, so this really is just going to be a quick pass just to see if there's any problems with the auto router, and maybe, you know, it'll give us an idea of how it's going to route things, and we can maybe move things around accordingly. So let's do that. And I've already installed the auto router plugin called FreeRouting. You can see this in previous videos. It's now a plugin easily accessible within KiCad 8 and onward, and basically it's installed, so it's actually quite simple to use. You just click the button. So as long as you've got the appropriate JRE, the Java runtime, already installed. If you don't have the Java runtime already installed, then it will install it for you. Okay, it's pulled in the project, and I'm just going to click start now. I'll make this window a little bit bigger so we can see what's going on. And as you can see, it's now gone ahead and started the auto route process. Like I say, it's default track widths, so it's not particularly very good. And that was it. Took about 5 seconds, something like that, and that's the board routed. A lot faster than you could do it manually. Now, what I need to do is look at the you know, how many vias have we got going on. There's quite a few vias here, and obviously all the track widths are the same, including the power. This power lead should actually, this power trace should be thicker as standard, and you'll notice it goes, the power goes all the way around here. It's going to the ADC there on the back side of the board, and it's going to whatever part that's for, a 10K. They're part of the reset circuit, in fact, and it goes to the MCU. You'll notice that the MCU is now being supplied by power. These tracks could all be a little bit thicker, that's all. Okay, so I've gone ahead and made some changes. I will have a look at the schematic first, and I'll show you what we've done here. Basically, we've added a transistor for the speaker driver, a very small addition of a decoupling capacitor across the power supply rail. And you'll notice that we now have a couple of different footprints for the both for the power connector. These are now screw terminals. We're going to get a much better connection than just using 2-pin headers. I think what we need to do now is actually, oh, and of course the other thing I haven't mentioned is I've changed some of the net classes, track net class. And you can do that up here if you go to this edit predefined sizes, and then go to net classes here. You'll notice I've added another class. This is the default track widths, which pretty much applies to everything. If you don't set anything, that's what you get for all of the track widths and via sizes. But I've added this one here. I've just made the clearance a little bit bigger. I've made the track 0.5 millimeter wide as opposed to 0.2, so it's wider. The via size is now 0.8 as opposed to 0.6, and the via hole size is bigger as well to suit the via size. So basically, those are an upgraded, if you like, a thicker track. When you come down to labeling or assigning the track widths, you use the plus button here, and you can assign what net you want to have, what net class. So the +5, anything with +5 rail on it, or +5 net, is now applied to this net class that I've called Power Plus, which is this one up here. Okay, so in other words, anything with the net class of +5V will now go to this width, all right, because we've called it Power Plus. What I'd like to do first is fill the board with copper, a copper fill on the top and the bottom. And the reason why we do that is because when it goes to the auto router, it will know that it's been filled and actually put the traces through that. So add a filled zone. You can also select Control, Shift and Z. And again, we've done this in other videos, and all you have to do is just kind of find the edges of your board, like there. This then plops up, and you want to select what I'm going to select is the top copper and the bottom copper to fill, so it's both ticked there, and the net is going to be ground, GND, so click OK to that. You can of course change the net to anything you like, but it makes sense in our case to go for a ground. And what I'm doing is I'm just going to the corners of the unit, of the PCB, and just outlining the entire board. I'm sorry if this looks like it's jumping around a little bit. I'm using the mouse wheel to zoom in, of course, but all I'm doing is scrolling around so I can get an accurate point. And here's the last one here. You can just see that one there. There. So that's then created a complete, you notice it puts this hash around, and what we're going to do is that's now covering the entire board, and we can then go ahead and select that hash and right click and go to zones and fill all zones. So it's zones and fill all zones. Okay, everything goes like pink. So what that means is we now have copper on the top and on the bottom, and if you switch everything off, the two layers in the layer selector up here, let's just have a look at the top copper. You can see it's all filled. Let's have a look at the bottom copper, and it's all filled as well. You get some interesting things like this where you have a ground connection and you have the spokes which connect to the thermal spokes that connect to the pads, and there's another ground one there. So that's absolutely brilliant. Straight away we've got all of our ground connections. Well, as you will find out, probably not all of them, but most of them. It doesn't always get it right. So next thing we need to do now is send this to the auto router, or of course you could do it manually as we said earlier. So I'll just save what we've got so far. So let's just send this to the auto router and let it do its business. Click that, and it's now loading in the PCB, and we'll tell it to continue. And of course we have got the class widths set up for the positive power rail, and there you go. Now what you'll notice is all of the copper is shorted out. There's no gaps or anything between the copper fill and the copper track, so we have to press B, which basically does another fill all zones. Let's do that, and there we go. Now we actually have insulation between the that's the positive rail there to the actual copper fill, and it's gone round and basically it's done everything. That's mostly done. I'll click save. So we're getting pretty close here, but what we'll have to do of course is run the DRC and just see what state we're in. You can guarantee there will be errors. Let's have a look and run the DRC. How many errors? That's the question. 6 errors. So, well, it's not too bad. 6 errors is not ridiculous. So let's work through these one by one. The spoke count should be 2 when it's only 1. So let's zoom in a bit and see where it's taking us. And that's where it puts the crosshairs, right on that chip pin just there. You see that, where it's gone sort of pink? So this is the first error. What it's telling us is, this is obviously the MCU, it's expecting 2 spokes, or 2 connections if you like, to this ground pin, and we only have 1 at the moment. If we click the little arrow there, it tells you down here, thermal relief connections to zone incomplete. Spoke count should be 2, actual 1. So it's telling us that there should be 2 connections. What it means is that this should be ground here as well. We've got the right hand side one, but there should be a 1 on the left. So what we can do there is simply add a wire here, like that, and then we can take a manual trace from there to there, and this will connect through to the blue side or the other side of the board, and that should give us a ground. So let's just select the manual route, and we can hopefully, right, it's not going to let me do that, so we're going to have to shift this track first. Let's pull him down here, and this is where the manual editor comes in. You know, let's put him somewhere down a little bit closer there. The manual editor in KiCad is actually very good. There you go. So I've added that track there, and I'm going to press B now to fill all zones, just to fix up the copper area. You'll notice we've now got this little copper area here, and it's connected to ground, which connects through to the other side of the board, which is ground. We had 6 errors, now we have 5, and the error's gone. Yeah, it's talking about the spoke count here. So again, we could either go up or we could go down, but we can't really go right. So I think if we zoom out a bit, we should be able to drag this track down, get it out. In fact, we can get it out the way of the crystal. It's even better. And I think we'll drag him down as well. Kind of a bit like that. And it should fill in this area here. Press B. There you go. And now we've got 2 spokes onto that ground. Let's just check we didn't actually break anything else in the process. Well, he can come further down and just tidy this up. It really is an iterative process of going through, pressing B. There you go, clean that up. That looks okay. And then we can go to the DRC, obviously, our good friend the DRC. And we're now down to 1 error. So that's not bad. This is the last error that we need to sort out. And what is this? 1 spoke connected to isolated island. Ooh, okay, so where's this? Here. Yeah, can you see that? It's absolutely right. 1 spoke connected to an isolated ground island. And there it is. This bit here is going nowhere. So we need to get this connected to ground. The easiest way to do this, I can see, is to pull this track down. It's going to make some space. We've got plenty of area here. Simple as that. Now press B to fill in this area. Boom. There you go. So now we've got the both connected. And if we're lucky, that's the end of all the errors. One last go. There. Everything's green. We've got no unconnected items and we've got no violations. So we can save that. This is now an electrically correct board. Now I'm going to keep going off camera because, as you can see, there are traces which are allowed. It's not an error. They do have the certain amount of clearance, but I just don't like it. You know, when you're soldering things, you don't want traces really close to pads. At least I don't anyway. So I'm simply going to go around the board and do things like this. Just get the tracks away and press B again. It was allowed, but I didn't like it. So you know, after a while, you just sort of get a feel for things. There's another one there. You see, we've got like a positive rail here. We can just drag that up there and get him well away from the other pads. Press B. That's clean. And so on. All right, so I've just spent probably 10 minutes or so just going around the various sections and seeing if there's anything that could be tidied up manually. I found a few things that looked a bit funny, so I've just sort of, like, you know, sorted them out. Ladies and gentlemen, I think we're ready to get this exported to Gerber files and plot files, and we can upload it to our favorite fabrication house and get the thing produced, get the thing manufactured. So that's where we are. I do believe we have completed the design process. Right, so I'm going to now export all of this. I'm not going to show the export to Gerber and plot files. We've covered this 2 or 3 times already in different videos. If you want to know how to do that, just watch one of the older videos, like possibly the CTCSS repeater video. I think I showed the export on that, and ones before that as well. So let's just leave it there. What I'm going to do now is stop the video. I'm going to get this exported and uploaded. The next time you'll hear back from me, we will have PCBs, hopefully. Takes about 10 days. Okay. And welcome back. After a few days of shipping time, we've got our PCBs. Always an exciting time, so let's get this open and have a look. And I haven't actually looked at these yet, so let's just see. And we get the usual packaging, and yeah, comes in plastic wrap. So let's break this open and have a look at the board, and let's see if we got it right, or did we make any errors. Ha! Ooh, there we go. There we are. It's looking pretty decent on the face of it, without looking too closely. Yeah, looking pretty good. Let's have a look at got the silk screen there. Let's have a look at the back. That's where the control will go. So let's see if our measurements and dimensions are correct. That's the next thing. Will the display fit onto that? Okay, so here's our display. So the question is, did we get the alignment right with all of the holes and everything, and the connector? So that's obviously the front, and this will go on the back like so. So let's just line this up, and you're seeing this in real time with me too. That's, oh yes. Now then, all of the mounting holes look perfect. Can you see through those holes there? So the mounting holes are correct. The edge connect is correct. Now you can see that the display goes on there, and that gives us a little area here for the rotary encoder. And I've got a bag of those here. So I just got a lot of eBay. So let's see if one of these fits. I'll try that, if I can get one out of the packet. And well, the pins are bent all over the place because it's been in a plastic bag, which isn't ideal. And let's see if we can get that in there somehow. So and that snaps into position. Look at that. It'll actually stay in because it's a snap fit, and it's absolutely perfect. Look at that. So that's going to be our rotary control, and then the display will go on there, as we've mentioned earlier. All of the holes line up. It's absolutely bang on. So far, excellent. It all lines up, and now you can see kind of how it's going to work. Once I get the connector in there, that'll basically be able to push into and onto there and fit with the connector. So what we really need to do next is take a close look at the board, and we can start to populate it. Let's get some parts on the board. So yeah, I found some standoffs, just some brass fittings here. They don't have to be brass, they could be plastic or nylon or anything like that, but these seem to fit quite well. I've got some socket headers here, which just arrived today. Theoretically that should fit into the board. You can see that. There you go. Perfect. So the way to solder this in is to actually bolt the whole thing together, and you know, put the actual connector together there. That'll locate this to the exact right angle, you know, and then we can solder the backside, and everything should be correct. Okay, so I've just loosely bolted the whole thing together, and that basically means that the alignment is now correct, and that just pushes nicely into the connector there. That means we can now go ahead and solder this connector onto the board. So let's do that now. Okay, let's do a bit of soldering. Here we go. Hope you can see all of this. When you solder to the earth, like the ground connections, you need a bit more heat, because it works a bit like a heat sink, and it sucks the heat away from the pin, like this one here on the end. I'll just retouch that a little bit. There you go, this one on the end. tends to take a bit more heat, and that's where the spurs come in. And when you remember looking at the footprint of certain ground islands, and because you've got like spurs, it's not a complete copper connection all the way around, like on the end pin here, which is the ground. So it helps to allow the heat to stay within the pin, and it's harder for it to actually cool down. There's our connector. So what we can do now is take the screws back out again, and the whole thing should just like come apart. I've took all the screws out now, so it's kind of loose there, and all we need to do now is sort of prise this apart. Ready? And that's it. So yeah, so now we've got a connector exactly at the right angle, you know, sticking up straight, which is correct for mating to the display. I've gone ahead and fitted the regulator and also the contrast potentiometer. I'm just about to fit the ADC module. I think the easiest way to do this is just to hold it like that and get the angle correct. And I'm just going to tack one of the pins, and that should hold it into place. So we'll just kind of like do it manually. So we'll just do one pin, and I'm just going to heat it up and orientate it the way we want it. There you are, about there. Let that cool down. That's fine. Then we can do another pin. Right, I'll solder this into place and we'll come right back. Okay, so that's now soldered and we've got it pretty flat there. You know, when I put the whole thing back together again, like that, and just push that back together, I think you can say there's a huge gap. I hope you can see inside of there. There's plenty of space. I don't even have to chop those legs off. There's kind of like no need. There's plenty of space in there. Just putting in some more parts here. Got the connectors in. Got the current control preset in there. It's coming along. So let's just keep going. Might do the ISP header next. Okay. ISP socket is on. I'm going to do the rotary switch now. Okay, so we've got the rotary switch, the rotary encoder data wheel pushed into position on the correct side of the board, making sure we don't put it on the other side of the board. Easy enough to do. So yeah, the display will be here and this is on the top. So we need to solder this into position. I'll do the earths first. The tags. Okay, it's the tags. Then we'll do the actual pins of the device. This is an earth pin with a couple of spokes. Needs a little bit more heat. Okay, and that's it. So 0 volts. I prefer 0 volts to ground. That just needs a little bit of a clean up with some isopropyl, and that's it. Switch is in. And when you've come to complete the whole project, or of course what we need is a vital component. We need an ECC 83 valve, and that'll just go in there nicely like that. Kidding. So far so good. I've got the ISP socket in, ISP header, got the speaker connection, serial comps port if we ever need it, LED. So the only thing that's left is some surface mount resistors and capacitors, 0805 footprint size, and the MCU, which should arrive tomorrow. Some of these parts haven't arrived. I'm just populating the board as and when things arrive through the post. Yeah, and just for the hell of it, I thought I would show you my little stash of SMD parts here in this shoe box or whatever it is. I tend to have all of the resistors here, all types, well not all types, but all the common types, you know, 1K, 4K, 7, 10K, that kind of thing. So, and I've got a lot of capacitors on this side, so yeah, that's my little selection of SMD that I tend to use for little projects like this. So I'm just going to use my tweezer set and and we'll take one of our 22 PF capacitors. These are going to go to the crystal, and yes, everything's very small. We're just going to place that roughly where we want to be, and you've seen us do this before. It's a standard way of doing it. And I'm going to use my fine solder and just put a little blob there on one of the pins. Take the capacitor and then just tack it into place on one side, just like that. Done. Okay, and then we can solder the other side. So I'm just going to position it a bit better. That's better, and then solder the other side of the cap. Hope you can see all of this. Just like that. That's now soldered into place. So now we can do the other capacitor. Again, little blob of solder. Take our 22 PF. I find this a little bit difficult because of the angle I'm having to work at, and I've got a camera in my face. And tack that in. Okay, and then press it down. That's it. Just finish it off. That's it. So, and there we have it. So we actually have a couple of 22 PF capacitors across the crystal to ground. Right, so we can now continue. Put some more resistors and stuff on. And I'll just get my my loop and make sure that actually looks okay. We'll have a look through there and make sure it all looks neat and tidy. Again, at the end, we'll finish off by cleaning up with some isopropyl alcohol and get rid of all the flux residue. Now, one thing I forgot to mention was, of course, it's always a good idea to print out the fabrication layer from the PCB design. Indeed, that's exactly what the fabrication layer is for. So if you print out the fabrication layer straight from the one of your Gerber file exports using the Gerber viewer in KiCad, you can actually use this as a template as a guide rather for when you come to populate the board. Alright, so that's the board populated except for the MCU, the 328P, and that should arrive tomorrow. Okay, so we've now got to the point where the components arrived. I managed to get our MCU. There it is here, just waiting to be populated onto the board, and it's going to go right in here. As I mentioned earlier, we've got a couple of options. We can just take the chip and you know, use a very fine soldering iron tip and just solder it in. That's usually what I do. But I managed to find some of my liquid solder in a syringe. So what we're going to do is give it a try. We'll see if we can do this with a heat gun. We'll try that method. If it doesn't work very well, there's a chance that my solder paste is actually too old. It's been sitting around for a while. Could be it's solid. And if that's the case, then we're going to have to do it with the soldering iron tip. But let's try and do it with a heat gun, and we'll give that a try. Okay, well, as suspected, my quick chip syringe has gone a bit crusty. So what I'm going to do is I'm going to try and just put some out of the tube on the end of a Q-tip and apply it manually. I'll give it a try. So I'll just try. This could end up being a complete mess. Let's just try it anyway. I reckon that's far too much. Remove the excess. You don't want too much on, because what happens is it will just bridge out when you come to solder it. Like I say, you wouldn't normally have to do this, but I've just ran out. And this has gone a bit hard, so yeah, that might work. Something like that. Bit of a mess. It's not ideal. Getting paste everywhere here. And my syringe is now all over the place, so I need to clean up. You really just want like a ring around all the pins. That might work. We'll clean it up as we go. Let's see what happens there. So let's get some hot air on and see if we can actually get the chip on. Okay, let's give it a try with some air, making sure that the chip is in the correct position and orientation. If this doesn't work very well, then I'll probably just have to start again and hand solder the thing. And I'm just moving the hot air gun around. Don't stay in one place for too long. Get a hot spot. It's just starting to melt now, if you can see that. It's just going now. You see that? It's quite a bit of copper area to heat up, you know. You can always give it a little bit of a nudge. Just give it a tap on the top. Make sure it's in the right position. Yeah, that looks pretty good actually. Turn off the heat. Now what we'll need to do is obviously clean it up, check for any shorts. I think I might have actually one here. Get a little bit of solder braid on there and just clean it up. Yeah, so I've just had a bit of an eyeball round the pins, gone all the way around, and had to touch up a couple. There was a couple of bridges, about 2 of them, and a little bit of solder braid or solder wick. Cleaned it up straight away, and that was it. So that's happy with that now. That's in. All we need to do now is clean it up with some isopropyl alcohol, and just sort of go around all the pins. Give it a clean. That takes off all of the flux residue, and we can clean up a couple of the other little components while we're at it as well. I'm probably going to go around the whole board and clean the whole thing later, but let's get the thick of it off for now and just get rid of all of that flux. Let that dry out, and the chip is in. So what it means is we now have a completed board, and there you are, it's in. Right, so the first thing I'm going to do is just make sure there's no shorts across the power supply, just using the meter. So let's just go across the 0 and 5 volt rail. Well, we've just got a little click, which is absolutely fine. That's from the capacitor there on the input. We know we don't have any dead shorts or anything nasty going on, so it should be safe to apply power. So let's do that. Alright, so the board is now powered up. I'm just going to check, make sure we've got power to the board. Yeah, we've got 5 volts there. No magic smoke, no disasters. So I think we're ready to go to the next step. Right, so let's put the 5 volts on. Hey, look, we have a backlight showing random characters. Well, 2 bars of characters. That's a good start. It even means our contrast must be somewhere near as well. But of course, there's no firmware in the chip, so we're not going to see anything. But what I can do is find my adjusting tool. We should be able to have a bit play with the contrast control on the back. But to be honest, it looks as if it's somewhere near already. So yeah, that's going that way. That's getting dimmer, fainter. Yeah, it's gone now. Would you believe it was actually set right? And that's going too far. Now you want to get rid of those black areas. That's about it there. Must have been mid travel point on the a lot of potentiometers are shipped brand new from the factory, usually in the center position. There you go. So the contrast is set. So that means we've got power to the display. We know the contrast is working. Just a default going on at the moment. There's no firmware, so let's go over to the computer, see if we can get some firmware into the thing. So this is the programmer, AVR ISP Mark II, it says on the back. So we can plug in the programming lead into the ISP socket, making sure we get pin 1 located at pin 1, which is on the top, and that just plugs in there like that. So now we can go over to the computer and we can hopefully get some firmware going on here. Right, here we are into the Arduino IDE. What we need to do is to see if we can upload. So we have to go to upload using programmer here because we're not using the serial comms type programming like what you do with Arduino boards. We're going straight to chip, so we have to use the programmer here. Upload using programmer. Let's see if we get any errors down the bottom here. Hasn't worked. Bad connection. I think it's using the wrong programmer. Just a moment. No, that's correct. We have a failure. Right. It's actually telling us that the target connection is actually reversed. And on closer inspection, yes it is. So when I plugged in the programmer, I thought pin 1 was on the top left pin. It's actually on the bottom right pin. That means we're going to have to check the PCB layout, and it looks as if I may have the connector in the opposite direction to what I thought it was. It doesn't really matter, but it does mean that we have to be careful when we put in the plug. It's round the other way. So I've just turned it round, and I will check the PCB layout in a moment. Let's just try this again and upload using programmer again. Let's see if we get any further this time. It says it's done. There was no errors. And I'm just glancing over my shoulder and I can see characters on the display. Woohoo! Let's go and have a look. Well, actually, just before we go and have a look at the LCD, let's just check out this footprint for the ISP socket. And yes, there you go. It's actually on the bottom right as pin 1. And I thought it was on the top left. I had the connector in the wrong way around. Luckily, the whole thing is designed whereas if you do put the connector in back to front like the wrong way around, it doesn't cause any harm, and was actually able to detect the error and report back to the Arduino IDE to tell you that actually the connector's around the wrong way. It's obviously a very common fault. And yes, I fell into the trap of myself and I put the plug in the wrong way around. There you go. All right, check this out. We have characters on the display. It's upside down, and I need to remove the ISP header, which I had in the wrong way around. So let's just disconnect this from the USB first, and then disconnect the programmer. That gets the programmer away, which has completely crashed the entire thing. So I just need to reset the power and restart the power. There you go. And there you have it. Now, it seems to be taking a long time to reset, and I think I know why. It's because I haven't actually programmed the fuses yet for the clock speed, and it's probably running on internal clock and divided or whatever. If I'm not mistaken, this should actually come out of a reset eventually, but we need to program the fuses with the fuse settings within the MCU to tell it we want an external 16 megahertz clock. I think that's what's going on. There we go. So everything's like very slow. It's probably using some internal slow oscillator. There, yes, it's working, but it's like super slow. And that's because, like I say, we haven't actually programmed the fuses. It doesn't know what the clock is supposed to be, and we need to tell it that we want a 16 megahertz external crystal. Right, so I've opened up this application, AVR Dudes. It's free to download, and it can communicate directly with the RSP programmer, which is great. You can send it raw hex files and program, and you can verify and you can read back and that kind of business. But what we're interested in is this part here for the fuse bits. If you click read, it's just read the fuse bits from the chip, and it says success, so it's read them. But these values here are incorrect, and what we need to do is change these. The L is for low, H is for high, E is extended, and LB is the lock bits. So we'll leave the lock bits alone because we don't need to copyright anything just yet. We're still developing, so we'll leave those alone. So really it's just the L, H and E fuses that need to be programmed. Now you can click this button here and it'll take you to a website where you can do calculations, where it'll actually work out with a calculator which bits you need to select. There's also a bit selector here, which allows you to select what you want to do. However, I do have the values already written down, and I believe what we need is, if this is right, is FF for the low, DF for the high, and the extended is FD. What that should do is, if I've got this right, if my notes are correct, if it's not, I'll have to do it again. It should give us an external oscillator clocked basically without any pre-scaling or anything like that. Also for anything over 8 megahertz. Well, that's correct, because we're running a 16 megahertz clock. So what we need to do now is write those to the chip. So let's do that right now. Okay, that's now done. And hopefully, if everything's worked, our device should actually be clocking at the correct speed. And when you reset the unit, it should only take a couple of seconds, and you should actually have a display straight away within a couple of seconds after the splash screen. I think it's 3 seconds at the moment we've got it set to. And here we are back again. So, well, first things first, it booted up and we've got a display. I need to disconnect the programmer, and it may crash the unit. Sometimes that happens when you disconnect it. What we're really interested in now is it clocking at the correct speed? And we know that by the splash screen time, it should be something like 2 or 3 seconds, not like it was before. So let's just disconnect the power with this extremely fancy switch I've got going on here. Put the power on. 1, 2, 3. There you go. Right. Fixed. So by changing the fuse programming, we've now selected the right clock speed and the right external clock, not the internal slower clock. So now it's running at full speed, 16 megahertz. Well, look, we've got this far. We've got characters on display, and what else can we do? And we've got our firmware in. Let's have a bit play with the control. What does this do? Aha! We can alter the set point. However, it looks as if it's going the wrong way. So it's actually back to front. I did check the polarity of the switch. I did actually get that figured out. But for some reason, when you turn it anti-clockwise, the number's going up. And when you turn it clockwise, the number's going down. Well, we can easily change that in firmware. That's an easy fix. We can just make it go the other way. But to be honest, sort of slipped up a bit there. Shouldn't really be going in that direction. When we hit the button, what does it do? I can't actually remember. Oh, I've got some temporary text just to say press and release, just to actually check the action of the button. Fantastic. Looking very good. So I think we're at the stage where we can probably start to give it some stimulus, you know, measure the current, set that for 10 milliamps. Make sure that's right first. So let's do that. So what we need to do is to check the current. So let's just go straight across, and we've got 5.7 milliamps at the moment. If you can see that okay, 5.7. I'm just going to adjust it so it's somewhere near 10. And that's going down, so go the other way. Adjusting beautifully. We're up to 8. And we'll just do a quick rough calibration to get it to 10. Don't forget we can set this to other values. Doesn't have to be 10. But for our test purposes, it's probably fine. Okay, there you go, 10.001. You can't get any closer than that, really. Right. Okay, so that's the current set with the current potentiometer. So I've just picked out a 1 ohm resistor. It's a double gold, so we'll check that on the meter and see what sort of value it's given us. 1.04, 1.02. Yeah, it's pretty accurate. Slightly over 1 ohm. Let's put this straight into the terminals of the where the probes go. Check it against this 1 ohm resistor. Okay, so now we've got the 1 ohm resistor in. Don't forget this will go to the box with a couple of probes. So let's try that. And I'm hoping I've fixed the direction of the wheel at the same time. We'll see. Switch it on. Okay, so little firmware change there, and it's all about going backwards and forwards between what we see and what the firmware is doing. We should now be able to adjust the set point correctly. Anti-clockwise goes down, clockwise goes up. That was a very simple firmware fix. Okay, I've connected up a little speaker here, tiny little speaker, and I've just got it on a couple of crocodile clips here just to try it out. I just hope nothing's actually shorting out here. Can't really see very good. I need to make a proper connector for it, obviously. DuPont connectors on it, and then we can try it. So we can check the sound either by setting off a bleep, or we can play the musical note at the beginning. So let's just try shorting it out. Yeah, that sounds okay. And by the time you put that in a box, that'll be loud enough. Oh yeah, that's way loud enough. Hey, the bleeper works. Yay. Let's try switching it off and switching it back on again. Let's try our little introduction sort of scale thing. When it starts. Yep, perfect. So that's where we are, and it's looking pretty good. That should go to 0-ish, well, 0.05, okay. All right, so a little bit more progress here. So, well, the first thing I've done is I've put some proper DuPont connectors on the speaker using our crimp tool. I think I showed a video some time back about how to make your own DuPont connectors there. So we've got one for the LED, that's now connected as well. Got a white LED, fancy, and we've got a speaker connected there. So everything's connected. We've got our test 1 ohm resistor just going in the end here. So let's have a look at the front panel. Okay, so now I'm going to connect the our test resistor. If you remember, it's 1 ohm, so it's below the set point. So this should activate. There you go. LED is flashing. Indicator bar is indicating, and speaker is bleeping. If you can hear that okay. Yep. Now, if we adjust the set point down to something just below 1 ohm, there's 0.95 of an ohm. Hope you can see all of this. 0.95 of an ohm. Let's connect the test resistor. And now it doesn't bleep because, well, we're above the set point. Our resistor is 1 ohm. It's actually telling us that we're 1.03 ohms there. So, hey, perfect. I think we've kind of won. So let's take that off. As long as you remember to disconnect the probes when you come to make an adjustment. You can't adjust it while the probes are, if you like, while the unit is bleeping. You could change the firmware, I suppose, if you wanted to include that, but to be honest, I can't really see a problem with it at all. Just open the probes and then you can make all the adjustments that you want. So I'll set that to just over 1 ohm. I'm setting it to 1.05 of an ohm, and our 1 ohm resistor is about 1.03, I think. Should alarm it. Yep, it's getting it. Perfect. Now, power supply wise, we haven't talked about that. You could run this off a 9-volt battery and maybe put it through some sort of a DC-DC converter to get it down to 5 volts. Another way of doing it is to use something very small, like a little 5-volt switch mode power supply. This operates from the mains in, 5 volts out. This is a 2 amp device. It's far more than we really need. We could easily power it by something like that. It wouldn't even warm up. And then you could plug the thing straight into the mains, put it in a a proper project box for a bench, in a bench type case. Build that inside with a power switch, and you've got yourself a whole unit in a box straight from the mains. So these are pretty cheap. They're only about £5 or something like that. Maybe it's a little bit more, £6. And 220 volts or 110 straight in, and 5 volts up to 2 amps, which is like far more than we actually need. But there you go, that would last forever probably. But like I say, we could make it battery operated. Another option is to have a USB connection coming in. Use a USB socket. That automatically gives you 5 volts from a computer. If you plug it into a computer, or you plug it into a dedicated wall supply, like a little adapter, and that will actually give you 5 volts through your USB lead, and that would power it up easily as well. So we've got loads of options. As long as we end up with 5 volts at around about 100 milliamps, we're good. So it's pretty easy to achieve. So really, because we know the hardware's done, we have a complete unit. How about that? I think we can give this a big thumbs up. Yes, it has actually worked. You could spend more time now implementing the push switch. You know, we've got a push button on here, and this could potentially adjust menus. You could have a menu selector. It's all about the firmware and programming from this point, and we can get to that possibly in a later video. We can take this further. One thing I would like to do with this is to be able to null it out. So when you short the probes together, maybe you hold the button for a couple of seconds or something, and then it'll go to a relative 0 reading. That would be a very useful feature. Then the readings are going to be accurate without any resistance of the probes or the connectors or anything. But for testing purposes, testing traces to say, okay, we can dial this in and take it down to say 0.3 of an ohm, something like that, 0.3 of an ohm. That's good for a lot of traces, and it's if your resistance is higher than that, you may have a problem depending on the length of the track. If it's lower than that, then you're good and you get a bleep. So hey, I hope you can appreciate we've kind of got to where we want to be. After this, there's only 2 things left to do. Put this in a box, okay, and then we can cross that off the list, get it in a box. And the other thing is firmware updates. Like I say, you could have a menu system, you could alter various parameters, you can turn the musical note on and off if you don't really want that when you first turn it on. If you don't want to hear that sound, which I'll do right now, and then you can, like that. So if you don't like that, maybe just put that on a menu, yeah, get rid of that, whatever. Lots of room for options here. I think for this video we're going to stop. Big thumbs up. We might come back to this and finish it and get it in a box. If you follow the channel, sometimes I put the odd post out with photographs and things where it sort of like gives you like an update, like a video short. Maybe I'll just put this in a box and show it as a finished product. But there we go. I think we're going to leave it there because this is a really long video now. We've done the entire process from idea, schematic, PCB, got the PCB manufactured, populated the board, put it all together, a little bit of debugging. There was 1 or 2 things like the wheel was going the wrong way and stuff like that. Sorted that out in firmware, and here we are. And it appears to be working. Fantastic. So if you've got this far in the video, thanks very much for watching. And you must be as nerdy as I am. And basically, we're going to leave it there, and I'll say goodbye. Possibly another follow-up video to this in a box, who knows, we'll see. Comment below, did you like this kind of thing? If you found it useful, give us a thumbs up. Please remember to subscribe to the channel if you're watching this and you liked it, then subscribe. Press the subscribe button-y thing. Okay, thanks very much, and we're going to leave it there. And here's to the next time. You take care. Bye-bye.